Welcome to this comprehensive guide on the sum rule in differentiation. I'm excited to walk you through one of the most fundamental and useful rules in calculus. Before we dive into the sum rule, let's quickly recall what differentiation means. When we differentiate a function like f of x equals x squared, we get f prime of x equals 2x. Differentiation tells us the rate of change of a function at any point. So what exactly is the sum rule? The sum rule states that the derivative of a sum of functions equals the sum of their individual derivatives. In mathematical notation, this means the derivative of f of x plus g of x equals f prime of x plus g prime of x. Let me show you a simple example to illustrate this concept. If we have 3x squared plus 5x, we can find the derivative by taking the derivative of each term separately. The derivative of 3x squared is 6x, and the derivative of 5x is 5. So our final answer is 6x plus 5. Why should you care about the sum rule? First, it dramatically simplifies complex differentiation problems by breaking them into manageable pieces. Second, it serves as a foundation for more advanced calculus rules you'll learn later. Third, it's absolutely essential for differentiating polynomials, which appear everywhere in mathematics. Finally, this rule has practical applications in physics for analyzing motion, in engineering for optimization problems, and in economics for marginal analysis. Here's exactly what we'll cover in this comprehensive video. First, we'll establish the precise mathematical definition and formula. Then, we'll explore how to extend the rule when constants are involved. Next, I'll teach you step-by-step application techniques that work every time. We'll work through detailed examples with both polynomials and trigonometric functions. I'll also highlight the most common mistakes students make and show you how to avoid them. Finally, we'll explore real-world applications so you can see why this matters. By the end of this video, you'll confidently apply the sum rule to any differentiation problem you encounter. Are you ready to master the sum rule? Let's begin our journey into this fundamental calculus concept. In the next section, we'll dive deep into the mathematical definition and see exactly why this rule works the way it does. Now that we understand what differentiation is, we can explore one of the most fundamental rules in calculus, the sum rule. This rule will make finding derivatives much easier when dealing with functions that are sums of simpler functions. The sum rule states a beautifully simple principle. The derivative of a sum of functions equals the sum of their individual derivatives. This means we can break apart complex functions and differentiate each piece separately. Mathematically, if we have a function f of x that equals g of x plus h of x, then the derivative of f with respect to x equals the derivative of g with respect to x plus the derivative of h with respect to x. To understand how this works, imagine we start with a function that is the sum of two simpler functions, g of x and h of x. When we want to find the derivative, we apply the derivative operator d dx to both sides of our equation. Here's where the sum rule comes in. Instead of trying to differentiate the entire sum at once, we can separate it into the derivative of g of x plus the derivative of h of x. This simplifies to our final result, f prime of x equals g prime of x plus h prime of x. We've successfully broken down a complex derivative into simpler parts. The sum rule extends beautifully to any finite number of functions. Whether you have 3 functions, 5 functions, or even 100 functions added together, you can differentiate each one separately and add the results. An important note, this rule also applies to subtraction. The derivative of g of x minus h of x equals g prime of x minus h prime of x. The sum rule handles both addition and subtraction seamlessly. But why does this rule work intuitively? Think about rates of change in everyday life. If one quantity is changing at rate A and another quantity is changing at rate B, then when you add these quantities together, the combined rate of change is simply A plus B. For example, if temperature is rising at 2 degrees per hour and humidity is rising at 3% per hour, then the sum of temperature plus humidity is changing at a rate of 2 degrees plus 3% per hour. The rates simply add together. The key takeaway is this. The sum rule allows us to differentiate each term separately, then add or subtract the results. This works because derivatives measure rates of change, and rates of change combine in a linear fashion. This fundamental principle will be the foundation for solving more complex differentiation problems. Now we'll extend the sum rule to handle constant multiples of functions. This is a powerful extension that makes differentiation even more flexible and useful. Here's the extended sum rule formula. When we have constants multiplying functions like a times f of x plus b times g of x, the derivative becomes a times f prime of x plus b times g prime of x. The key insight is that constants can be factored out of derivatives. This works because differentiation is a linear operation, meaning it preserves addition and scalar multiplication. Let's work through a concrete example. We want to find the derivative of f of x equals 5x squared plus 3x. Step 1. We apply the sum rule to separate this into the derivative of 5x squared plus the derivative of 3x. Step 2. We factor out the constants. The 5 comes out of the first derivative and the 3 comes out of the second derivative. Step 3. We apply the basic derivative rules. The derivative of x squared is 2x and the derivative of x is 1. Step 4. We simplify. 5 times 2x equals 10x and 3 times 1 equals 3. So our final answer is 10x plus 3. Notice how the constants 5 and 3 from the original function became multipliers in our final derivative. This demonstrates the power of the extended sum rule with constants. The key takeaway is that constants multiply the entire derivative of their respective functions. This makes the sum rule incredibly powerful for handling complex polynomial expressions and other functions with constant coefficients. Now we'll work through our first example to see the sum rule in action. We need to find the derivative of f of x equals 3x squared plus 5x minus 7. Step 1 is to identify each individual term in our polynomial. We have 3 terms, 3x squared, 5x, and negative 7. Each of these terms will be differentiated separately. Step 2 is to apply the sum rule. The derivative of the entire function equals the derivative of 3x squared plus the derivative of 5x plus the derivative of negative 7. This is the fundamental principle of the sum rule. Step 3 is to differentiate each term individually. For 3x squared, we use the power rule. Bring down the exponent 2, multiply by the coefficient 3, and reduce the exponent by 1, giving us 6x. For the second term, 5x, we again use the power rule. The exponent is 1, so we get 5 times 1, which equals 5. The x to the power of 0 becomes 1, so our result is simply 5. For the third term, negative 7, this is a constant. The derivative of any constant is always 0, because constants don't change as x changes. Step 4 is to combine all our results. We have 6x plus 5 plus 0. Since adding 0 doesn't change anything, we can simplify this to our final answer. Therefore, the derivative of f of x equals 3x squared plus 5x minus 7 is f prime of x equals 6x plus 5. This demonstrates how the sum rule allows us to break down complex polynomials into manageable pieces. Remember, the sum rule process is always the same. Break the function apart into individual terms, differentiate each term separately, then combine the results. This systematic approach works for any polynomial function. Now let's work through our second example, which involves trigonometric functions. This will show you how the sum rule applies to more complex mathematical functions beyond simple polynomials. Here we have the function f of x equals sine of x plus cosine of x plus 2x. Our task is to find the derivative of this function using the sum rule. Step 1. We apply the sum rule. The derivative of f of x equals the derivative of sine x plus the derivative of cosine x plus the derivative of 2x. Notice how we can differentiate each term separately. We have 3 separate terms to differentiate. Let's work through each one individually. Step 2. Now we calculate each derivative separately. First, the derivative of sine x is cosine x. Second, the derivative of cosine x is negative sine x. Remember the negative sign. This is crucial for trigonometric derivatives. Third, the derivative of 2x is simply 2, since the derivative of x is 1, and we multiply by the constant 2. Step 3, we combine all our results. The derivative f prime of x equals cosine x plus negative sine x plus 2. We can simplify this by writing negative sine x as minus sine x. So our final answer is f prime of x equals cosine x minus sine x plus 2. Here's the key insight. The sum rule works perfectly with trigonometric functions. Each trigonometric function follows its own derivative rule, and then we simply add the results together. This demonstrates the power and flexibility of the sum rule in calculus. So we've successfully applied the sum rule to a function containing both trigonometric and polynomial terms, showing that the rule works seamlessly across different types of mathematical functions. Now that we've seen how to apply the sum rule, it's crucial to understand the most common mistakes students make and how to avoid them. Being aware of these pitfalls will help you apply the sum rule correctly every time. The first and most common mistake is sign confusion, especially when dealing with subtraction. Let's see this mistake in action. Consider this function, f of x equals 3x squared minus 5x plus 2. Let's see what happens when we make the sign error. Here's the incorrect approach. The student forgot to keep the negative sign when differentiating negative 5x, writing plus 5 instead of minus 5. The correct approach preserves the negative sign. The derivative of negative 5x is negative 5, not positive 5. Prevention tip: always write out each term separately first before combining them. This helps you keep track of signs. The second common mistake is forgetting that constants factor out when differentiating. Remember, the derivative of c times f of x equals c times f prime of x. Consider this function, g of x equals 4x cubed plus 7x squared. Here's the incorrect approach. The student forgot to multiply by the constants 4 and 7. The correct approach keeps the constants. 4 times the derivative of x cubed is 4 times 3x squared, which equals 12x squared. 7 times the derivative of x squared is 7 times 2x, which equals 14x. Prevention tip: constants always stay with their terms throughout the differentiation process. Don't drop them. The third mistake is confusing when to use the sum rule versus other differentiation rules, like the product rule or quotient rule. Use the sum rule when functions are added or subtracted, like x squared plus sine of x minus 3x. Don't use the sum rule when functions are multiplied or divided. For x squared times sine of x, use the product rule. For x squared divided by sine of x, use the quotient rule. Prevention tip: look for plus and minus signs between separate functions. If you see multiplication or division, you need a different rule. Here's a summary of prevention strategies. First, use color coding for different terms to keep track of them visually. Second, write parentheses around negative terms for clarity. Third, work step by step and don't rush through the problem. Fourth, always double-check your signs before finalizing your answer. And fifth, identify whether functions are added, subtracted, multiplied, or divided before choosing your differentiation rule. By being aware of these common mistakes and following these prevention strategies, you'll be much more successful when applying the sum rule. Practice and careful attention to detail are your best tools for avoiding these pitfalls. Now that we've mastered the sum rule, let's explore how this fundamental concept applies to real-world problems across different fields. The sum rule isn't just an abstract mathematical tool. It's essential for solving practical problems in physics, economics, and engineering. Our first application comes from physics, where the sum rule helps us analyze motion. When we have a position function that describes an object's location over time, we can use the sum rule to find velocity and acceleration. Consider an object whose position is given by the function s of t equals 4t cubed plus 2t squared minus 5t plus 1. Where s is measured in meters and t in seconds. To find the velocity function, we take the derivative of the position function. Using the sum rule, we differentiate each term separately. Applying the sum rule, we get the derivative of 4t cubed is 12t squared, the derivative of 2t squared is 4t, the derivative of negative 5t is negative 5, and the derivative of the constant 1 is 0. For acceleration, we take the derivative of the velocity function. Again, using the sum rule, 12t squared becomes 24t, 4t becomes 4, and the constant negative 5 becomes 0. This demonstrates how the sum rule enables us to analyze motion systematically, breaking down complex position functions into understandable velocity and acceleration components. In economics, the sum rule is crucial for analyzing cost functions and finding marginal costs. Marginal cost tells us how much the total cost increases when we produce one additional unit. Consider a company with a total cost function C of x equals 0.01 x cubed plus 2x squared plus 50x plus 1,000, where x represents the number of units produced and c is the cost in dollars. The marginal cost is the derivative of the total cost function. Using the sum rule, we differentiate each term. 0.01x cubed becomes 0.03x squared, 2x squared becomes 4x, 50x becomes 50, and the constant 1,000 becomes 0. This marginal cost function tells us exactly how production costs change as we increase output. For example, when producing 10 units, the marginal cost would be 0.03 times 100 plus 4 times 10 plus 50, which equals $93 per additional unit. This economic application shows how the sum rule helps businesses optimize production by understanding how costs change with output levels. In engineering, particularly signal processing, the sum rule helps analyze composite signals. Engineers often work with signals that are combinations of multiple waveforms. Consider a composite signal f of t equals 3 sine of 2t plus 2 cosine of 3t plus 5. This represents a signal with two oscillating components plus a constant offset. To find the rate of change of this signal, we apply the sum rule along with the chain rule. The derivative of 3 sine of 2t is 6 cosine of 2t. The derivative of 2 cosine of 3t is negative 6 sine of 3t, and the derivative of the constant 5 is 0. This derivative function tells engineers how quickly the signal is changing at any given time, which is crucial for signal filtering, modulation, and other processing techniques. These three applications demonstrate the versatility and importance of the sum rule across different fields of study and professional practice. As we conclude our comprehensive study of the sum rule and differentiation, let's recap the key points that will serve you well in your mathematical journey. First, remember that the sum rule states, the derivative of a sum equals the sum of the derivatives. This fundamental principle applies to any number of terms and works with constant multiples. Second, always work systematically. Identify each term, apply the appropriate differentiation rules to each term separately, then combine the results. This methodical approach prevents errors and builds confidence. Third, pay careful attention to signs, especially when dealing with subtraction. Remember that subtracting a function is the same as adding its negative, so the sum rule still applies. Finally, practice is essential. The sum rule appears in virtually every calculus problem involving derivatives, so mastering it early will make all subsequent topics much easier to understand. The sum rule is more than just a mathematical technique. It's a powerful tool that opens doors to understanding motion in physics, optimization in economics, and signal analysis in engineering. Master this rule, and you'll have a solid foundation for success in calculus and beyond. Thank you for joining me in this exploration of the sum rule. If this video helped clarify these concepts for you, please give it a thumbs up and subscribe for more calculus tutorials. Leave a comment below if you have questions or suggestions for future topics. Keep practicing, stay curious, and remember, every expert was once a beginner. Until next time, happy calculating.